So good morning, myself Swapnil Raut, and this is my demo video, and I will discuss some topic which is related to the VBT and CFT. Okay, so let us start. So, as you know, in the chapter coordination chemistry, in this chapter, Alfred Werner, who is called as a father of coordination chemistry, he told us about the primary valency, about the secondary valency, about the coordination number. Basically, he introduced with us the metal complexes. Okay, but bonding in between metal and ligand, he is not clear about that what kind of bond is this. So for deeply knowing the bonding in between metal and ligand, we study different theories like valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory. Okay, so by studying different theories, we are able to know that what kind of bonding is present in between metal and ligand, what kind of orientation, what kind of stereochemistry, what kind of magnetic properties, optical properties, color, spectra, everything. So now let us discuss bonding in a coordination complexes. Okay. For knowing bonding in coordination complexes, we have to study first VBT and then CFT. In our syllabus, only these three we have to study first. Okay, VBT and CFT. These are the theory which I will explain. I will explain the concept, that is why ligands are metal complexes are high spin complexes, low spin complexes, and why there is a pairing occur in between complexes, while ligand field pair the electrons. Okay, and why some ligands not able to pair the electrons. That concept I will discuss here. So with the help of VBT and CFT, I will explain that concept. So now let's discuss the VBT first. I have to introduce you with some points from the VBT. Then I will use that point to explain my concept, to explain my concept basically. So VBT means what? Valence bond theory. Valence shell, using valence shell electron of metal. So basically what happened here, in valence bond theory we use concept of hybridization. We use concept of hybridization. Okay. Use concept of hybridization. Okay, as we know, hybridization means what? Intermixing of atomic orbitals of near about of same energy to form new set of equal and new set of hybrid orbitals. Okay. So by the help of hybridization, we can see a bond in between metal and ligand. Okay. So basically in metal and ligand, by VBT assumptions, we said that the bond is totally polar covalent bond. Bond is totally polar covalent bond. Okay, that metal ligand, this bond is totally polar covalent bond. It don't have any kind of ionic character. It don't have any kind of ionic character. Okay, so this is a polar covalent bond. And in the valence bond theory, let us take example. First is the NaCnO4. And I will take second example with having metal is same. So in both cases, if you want to find the oxidation state of a nickel, so it is in a +2 oxidation state in both cases. Okay, you can find. I am finding. Let us find for this complex. X for nickel, then 4 into each cyanide ion, U1 minus negative charge. Okay, will donate 2 electrons, -1 charge. Okay, then 4 have minus 4 is equal to -2. Therefore, X is equal to -2 minus plus 4 is equal to +2. Okay, +2. Similarly, in this case also, the oxidation state for nickel is 2 positive. Okay, oxidation state of nickel is 2 positive. Same for both complex. Okay, so from that, as we know, atomic number of nickel is 28. Means electronic configuration will be for the Na2 positive will be argon means 18, 19, 20 and 8. Okay, 4s to 3d 8. Okay, so after removing 2 electrons, that will be for Na2 positive argon 3d 8 4s 0. Okay, this is same for both this and this complex also, because both complex have nickel is in a +2 oxidation state. So for knowing bonding in between metal and this ligand, nickel and this ion, we have to see what kind of how this bond form. So we have to draw some orbitals. Okay, these are the 3d orbitals. This is the 4s and these are the 4p orbitals. Okay, and in this orbital we have 3d8 now. 3d8 4s 0. Okay, so you have to fill 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, then as we know, Cn negative ion, cyano ion, each ion will donate -1, means 2 electrons basically. Each ligand will donate 2 electrons. We have 4 ligands. Then how many electrons will donate by ligand? 8 electrons. Okay. So for donating 8 electrons, we need 8 empty orbital. And we know that for hybridization, we have sp, sp2, sp3. Okay, sp3, d, d2, sp3, mini hybridization. So we can see here you have to form 4 bonds. So listen here. This ligand, this ion, okay, basically is a strong ligand. Cyano ion. This is a strong ligand. and Cl negative. Okay, this ion is a weak ligand. Okay, this is a chloro ion, cyano ion, chloro ion. So this is a weak ligand. Okay. So what happened? In the presence of strong ligand, these electrons will get paired if necessary. Just see here, this ligand will get paired with this. Okay. So we got one empty orbital. Okay. Then by using this one orbital, and these two orbitals, because we need 4 orbitals. Okay, this one, then another one, then these two. Okay, so what happened after that? These 4 orbitals get intermixed and form new hybrid orbital, which having as dsp2 hybridization. This is d orbital, this is s, and 2p orbital. dsp2 hybridization. Each hybrid orbital is dsp2 hybridized. Each hybrid orbital have all character of dsp orbitals. Okay, so here is a new 4 orbitals form, which having characters of all these 3 orbitals. Okay. So we have 8 electrons fill here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So you can see here. I can write this at this position here. One, two, three. Okay. So in this complex, we don't have unpaired electrons. And you can also notice one thing here. This complex is called as an inner orbital complex because we used here inner orbital for the hybridization, for the use of ligand. Okay, for the donation of electron from the ligand. And second thing is, this is also called as the low spin complex. Why low spin complex? Because number of unpaired electron decreased. Okay, it is called as a low spin complex, inner orbital complex. Okay, also called as a spin paired complex. Okay, so this is one example in which cyano ion is a basically strong ligand. That's why pairing of electron was happened. Okay, so now let's understand another complex. In this complex, you can see chlorine. This is Cl negative chlorine. This is a weak ligand. So this ligand is weak ligand, and because of that, if I am drawing outer orbital electronic configuration, so as we know, nickel to positive state, oxidation state, having 8 electrons. Let us fill following by Hund's rule. Okay, I have to draw one extra orbital. Okay. Two, three, 4, 5, 7, 8. Okay. So you can see here, these are the d orbitals. Okay, this is a s orbital, this is p orbital. Okay, for this complex. So each Cl ion donate 2 electrons. We have 4 Cl ions, will donate 8 electrons. But what happened here? Because of that weak ligand, the electron will not pair. So that's why this orbital will be not utilized by the ligand. Okay, so we have to use another 4 orbital to do hybridization. Okay, for the hybridization we use this S and 3 p orbitals. Okay, so hybridization will be sp3. I am drawing here 4 orbital intermixed to form new set of hybrid orbital having sp3 character. Hybridization also sp3, and 4 electron will be ligand will donate 4 electron in this orbital. 8 electrons, sorry, by the 4 ligands. Okay, so you can notice here it contains 2 electrons. Unpaired electron means it is a paramagnetic. Previous was diamagnetic here because they don't have unpaired electron. It has a 2 unpaired electron, means it is a paramagnetic in nature. And after that there is no pairing, and a complex is outer orbital complex. High spin complex because it has unpaired electron. Okay, and also outer orbital complex. High spin complex. Okay, so these are the 2 examples I have taken here. Basically only for showing that because of the ligand field there is a pairing of electron, and here in the previous case there was a pairing in the previous case, and here is not any kind of pairing. This is because of type of ligand we use. Okay, but VBT, these are only the assumptions of VBT. VBT was not able to explain properly why some ligands are weak ligand, why some ligand are strong ligand, why some are high spin complexes and why are some low spin complexes, why there is a pairing occurred. Okay, so for finding the answer, we have to study another theory called as the crystal field theory. Okay, so now let's go toward new theory called as crystal field theory. Let us elaborate it. Crystal field theory, very important theory and very interesting theory called as crystal field theory. Okay, so in this theory, this is the theory of a solid state physics. Basically it is a state of physics. Okay, we are using here to know what kind of bond is present in between metal and ligand. I know, or I accept that CFT is not properly explained, what kind of what actually bond is present in between metal and ligand. CFT told us that bond present in between metal and ligand is an ionic bond, and the interaction present in between metal and ligand is electrostatic interaction. It is the theory of solid state physics. CFT not able to explain properly what kind of bonding is present in between metal and ligand. Okay, that bonding is actually explained by ligand field theory, and ligand field theory follow Fajan's rule. Fajan's rule told that any bond have both character, that is ionic as well as covalent, but VBT explained us that it has only covalent character. CFT explained us that it has only ionic character, but actual condition, the truth was told by LFT. That bond has both covalent as well as ionic character. Ionic character followed by covalency. So let us discuss this theory. In this theory, metal and ligand. Okay, so if this ligand is too far from the metal, basically we call ligand as a point charges. We call ligand as a point charges. Okay, small tiny charge. Okay, ligand may be neutral or ionic. They contain negative charge as well as neutral. Okay, so when this ligand is too far from the metal, then at that time there is a primary attraction in between metal and ligand. Okay, in between them there is a primary attraction, means metal and ligand will approach towards each other, and after that what happened, along with this primary attraction there is a secondary repulsion. In between this ligand field, this ligand field. Okay, and metals orbitals. In between these two there is the repulsion. Okay, so when ligand is far from the metal, the repulsion in between orbitals and ligand is having spherical symmetry. That repulsion having spherical symmetry means what? That ligand field strength is in a having spherical symmetry. Basically, from all side orbitals of metal will experience equal symmetrical ligand field strength. Okay, but when ligand comes close to the metal, then at that time the orbitals, basically the d orbitals, which having a lobe on the axis like dz square and dx square minus y square, these orbitals having lobes on the axis, and this orbital experience more repulsion from that ligand field as compared to the lobes or the orbitals such as dxy, dyz and dxz. These orbitals, they have a lobe in between the axis. Because of that, the orbitals, the lobes will not experience more repulsion. I am explaining. You can see here, if this is a xy, okay, this is the xy orbital. So you can see here, you can change xy, yz, xz. Okay, so basically lobes are in between the axis, and in case of dx square minus y square, lobe is on the axis. Because of that, if ligand is here, okay, then this ligand field is more experienced by lobes on the axial position as compared to the lobes which are in between the axis. Okay, so because of that, there is splitting of d orbital. Because of that, there is a splitting. So let us discuss the splitting in the d orbital. Before going to the splitting, I have to explain some basic important thing, that s orbitals, p orbitals, outers, basically outer, and d orbitals. Okay, so ligand field strength is more applied on the d orbital than p, and negligible to the s. Okay, so splitting is more in the d. Okay, so now let us discuss splitting in p orbital. You can see here, these are the p orbital, px, py, pz. Okay, if ligand is there and this field strength experienced by all these three orbitals equally, means what? Lobes of this p orbital, like for all these three orbital, lobes are on the axial position. Because of that, each and ligand means each lobe experience same and equal repulsion from the ligand. Okay, so there is a true excitation. Okay, true excitation of the orbital because of the repulsion in between orbitals and ligand. There is a true excitation, increase in the energy, and these orbital are in the excited state. This orbital will go in the excited state, true excitation. But in case of d orbitals, in case of d orbital, this is not true. Means what? When ligand is near to the orbitals, these are the d orbitals in isolated gaseous metal, isolated gaseous metal ion. Basically isolated isolated gaseous metal ion. So in this case, when ligand is near to this orbital, when ligand field is experienced, I can say when ligand is far, and applying spherical symmetrical field is spherically symmetrical, then each and every orbital will explain same repulsion. Correct now? Ligand field explained by all the orbital is same. Because of that, there is a pseudo excitation. And all the orbital excites. Okay? And after that, when ligand is near to this orbital, then after that what happens? Then there is a true excitation in the orbital. Means what? Then there will be the splitting. And those orbitals which are on the axial position, if suppose this is the dxy, dxy, dyz, dxz, dx square minus y square, dz square. Okay, these are the axial, these are the non-axial. Okay, axial orbitals, non-axial orbitals. Okay, so those orbitals lobes of those orbitals which are on the axis experience more repulsion. So because of that, they have more energy. Okay. Because of that, splitting will occur in the orbital, and there is a true excitation. Because of that, this degeneracy means orbitals of same energy will split into two sets. First is the non-axial set, non-axial orbitals, that is dxy, dyz, dzx, called as the T2G. G for J-ray. It is based on the symmetry of complexes. COS basically, center of symmetry. Depend on center of symmetry of complexes. Okay. Basically, we are studying here octahedral complex. Which complex? Octahedral complex having 6 ligand. Okay. Suppose this is complex ML6. Okay, having 6 ligand and having this is octahedral complex having octahedral symmetry in the complex. Okay, so because of that, what happened in this complex? Non-axial orbitals, lobes, orbitals will have less energy, and orbitals which are on the axial position, side, they gain energy. Okay, they gain energy. T2G easy. Okay, so these are the orbital which having lobe on the axis, and these are the orbital which have lobe in between the axis. So these orbital experience more repulsion as compared to these orbital. So that's why they are in the higher energy side, and these are in the lower energy side. And this is the Berry center. This is the Berry center, called as the Berry center. And what amount of splitting is was happened? The difference in between these energies, this difference in between these two levels, energy difference in between these two levels is denoted by delta, and for octahedral we use subscript O. This is called crystal field splitting. This is called crystal field splitting, denoted by delta, also called orbital splitting. Crystal field splitting or orbital splitting means splitting of orbital. Okay, so denoted by delta. Okay, so this is the splitting. Okay, you can see here, this is a diagram which is used to. So what we have to do now here? So if we have to fill the electron, these are the orbital for the metal ion. Okay, after when ligand approaches that octahedral symmetry. Okay, so when ligand approaches the metal, when ligand is near to the metal, then this orbital gets splits into these two kinds of orbital. Okay, so when so after that, if I can say we have to fill electron first here, then here. I will explain this now. I am explaining this. Just listen here. We know that we have to follow many rules. First is the above rules, then Hund's rule. Okay, so above rules means what? We have to fill electron in those orbital which having low energy as compared to the orbital which having high energy. So we have to first fill these orbitals, then these orbitals, and by the principle of Hund's rule, we have to first fill single electron in this degenerate orbital, then pairing. We have to do pairing. Okay, so if I am considering three examples, if d orbital have 1 electron, then 2 electron, then 3 electron, then 4 electron. Okay, d having 1 electron, then 2 electron, then 3 electron, then 4 electron. So you can see here, if I am taking here 1 electron, so this electron by the rules you can fill here. Okay, if 2 electron here, if 3 electron here, and then 4 electron. If I am taking D4 configuration of a metal, then what happens? 4 electron can take this position as well as this position. Okay, as well as this position, this or this. But as we know, this is the half-fill configuration, and half-fill configuration is more stable. So if we have to, if we want this electron here, 4th electron is here, then there is a two kind of energies we have to are like a barricade. Basically, what I mean, this half-fill configuration is stable because of the exchange energy. Okay, because of the exchange energy means the electron get exchanged in between this orbital. Because of that, it get more stable. Okay, and second is the repulsion energy in between these two electrons. When I am adding this electron here, there will be repulsion in between these two electrons. So because of that, to add this electron here, we have to discuss two conditions. Okay, let us discuss that condition. First condition is that this delta for octahedral. Okay, if this delta is greater than pairing energy. Pairing energy is what? Amount of energy required to pair the electron, means amount of energy required to add that 4 electron to this. Okay, to pair the electrons. So for pairing, you can see here, this is the octahedral splitting, crystal field splitting. Okay, if this delta value is greater as compared to pairing energy, means what? There is more splitting. More splitting means there is a more difference. Okay, so this distance is more. So for transition of electron to this, okay, for adding this electron to this is more difficult. So electron will take this position. Means what? In simple word, if delta is more as compared to pairing energy, then pairing energy is less. Then means what? Amount of energy required for pairing is less. Because of that, pairing energy is less. Because of that, electron will add here. So amount of energy required for pairing the electron is less. That's why electron we can add here. But if delta is, if pairing energy is more as compared to delta, if this distance is small, if this distance is small, then and pairing energy is more, then what happen? Then exchange energy, then we have this configuration will be more not very stable as compared to this configuration. So we have to add that electron here. Means what? If pairing energy is more, energy required for the pairing of electron we require more. So why we are we have to, means what? We have to stabilize the complex. So for stabilizing complex, we have to need we need a low energy. We don't want extra energy. So that's why electron will go here to stable the configuration. Okay. So when electron is here, then that complex is called as a low spin complex. And when electron is here, called as a high spin complex. Low spin complex, high spin complex. Okay. I think you remember this thing. We discussed these two things in the VBT, that some complex from high spin complex, some complexes, some ligand from low spin complex. So you can see here that low spin and high spin is depend on the value of delta and pairing energy. That high spin and low spin property of the complex depend upon that the crystal is splitting, how much that splitting occur, and pairing energy, amount of energy required for the pairing. Okay, so these two are factors affecting these what I can say, pairing in the electron, pairing of electron in the complexes. Okay, so now let us discuss factors affecting this delta. Factors affecting this delta. So delta is basically, from the metal point of view, delta is depending on effective nuclear charge, means oxidation state of the metal. Means what? If any complex, if I am taking two complex and one complex have more positive charge as compared to second, then this will be more stable as compared to this, because this having more effective nuclear charge, Z effective nuclear charge as compared to this. Okay, so while going from top to bottom, means from 3D to 4D to 5D. Okay, if you can see here, because of the lantern contraction or because of the another contraction, okay, because of that, as we are going from 3D to 4D to 5D, what happened? Size remains nearly to equal, but number of proton increases. And number of proton increase means what? There is an increase in the effective nuclear charge, Z effective. That means that what it means? It means that this complex, means ligand attached to this complex having this metal ion is more stable as compared to, means 5D is more stable as compared to 4D, and 4D is more stable as compared to 3D. Why? Because of the effective nuclear charge is more here than here, less here, and very less here. Okay, this is from metal side, but from ligand point of view, delta is depend on ligand field strength. Delta is depend on ligand field strength. So in VBT we said that this ligand is strong field ligand, Cn negative ligand, a strong field ligand, chloro ligand is strong weak field ligand, cyano ion is a strong field ligand. So all this stuff we can basically depend on the ligand field strength. Okay, this is a relative phenomena. So basically CFT gave us spectrochemical series which is more logically explained by LFT, in which first is the pi donor ligands, then sigma donor ligand, and then pi acceptor ligand. So in this series, as I told you, it is on higher side and it is on the lower side. Okay, that's why this having more ligand field strength as compared to this, but this data for this delta is the experimental data basically from the spectrochemical data, spectral data. It is a spectral data. We can find this data by the by using spectral properties. Okay, and ligand field for as I told you that this delta is depend upon the ligand field strength, and ligand field strength, to know the ligand field strength of different ligand, CFT just assembled all the ligand and by their spectral properties basically they arranged all the ligand in a proper way, and that series CFT named as a spectrochemical series, means having different spectral properties basically, and some ligands are pi acceptor, some sigma donor and pi donor. So those ligands which are pi acceptor are the strongest ligand as compared to pi donor ligand, and sigma donor is in middle, in between there. Okay, so this is the basically all about my topic, today's topic, and thank you for being with me.